So, here's something worth thinking about as you settle in tonight. Right now, wherever you are, there's a quiet hum running through the walls around you. You probably can't hear it. You've spent your whole life not hearing it. But behind the plaster, behind the paint, there are copper wires carrying something invisible, something we've only really understood for about 200 years. And that invisible something is powering the light. You maybe just turned off the device playing this for you, the refrigerator keeping your food cold in the next room. Electricity. We say the word like it's simple, like it's obvious. But if you actually stop and ask yourself what electricity is, not what it does, but what it actually, fundamentally is, you end up in a surprisingly deep place. And that's where we're going tonight. Slowly. No rush. Just the story of how people figured out one of the strangest, most powerful forces in the universe, and how they learned to make it do useful things. Let's start way back. Not with wires and generators, but with a guy rubbing a piece of amber on his cloak. The year is roughly 600 BCE, and we're in ancient Greece, in the city of Miletus, on the coast of what's now Turkey. There's a philosopher there named Thales. You might have heard his name before. He's one of those pre-Socratic thinkers, one of the first people in the Western tradition to try explaining the natural world without just saying the gods did it. Thales was curious about everything: water, magnets, eclipses, and at some point, he noticed something peculiar about amber. Amber is fossilized tree resin. It's that warm, golden, translucent stone you sometimes see in jewelry. The Greek word for amber was electron. Remember that. It matters. What Thales noticed was that if you took a piece of amber and rubbed it vigorously against animal fur or wool, the amber would then attract small, light things, little bits of straw, feathers, dust. You'd rub the amber, hold it, near some chaff, and the chaff would jump toward it, cling to it, as if the amber had become temporarily alive with some invisible reaching force. Thales didn't know what to make of this. He speculated that amber might have a soul, that rubbing it somehow awakened a living quality inside the stone, which sounds strange to us now. But think about what he was working with. He had no framework for invisible forces, no concept of charge or fields or electrons. He just saw dead matter reaching out and grabbing things, and he tried to explain it with the tools he had. And here's what's interesting. For roughly the next 2,000 years, that's about as far as anyone got. 2,000 years. People knew amber did this weird thing. They knew lodestones, naturally magnetic rocks, did a similar but different weird thing, attracting iron. And they mostly just filed both of these under mysterious properties of certain materials and moved on. There was no sustained investigation, no systematic experimentation. The amber trick was a curiosity, a parlor demonstration, something to show guests at dinner. It's a good reminder that knowing about a phenomenon and understanding it are completely different things, separated sometimes by millennia. So let's jump forward. It's the late 1500s now, and we're in England, and there's a physician named William Gilbert. Gilbert was the personal doctor to Queen Elizabeth I, which tells you he was accomplished and well-connected, but his real passion wasn't medicine. It was natural philosophy. And in 1600, he published a book called De Magnet, On the Magnet, which is one of those books that quietly changed everything. Gilbert was obsessed with magnetism. He wanted to understand why compass needles point north, and he built these beautiful little spherical magnets he called terrellas, little Earths, and used them to model how the Earth's own magnetism might work. That alone was groundbreaking. But tucked inside, his work on magnets, Gilbert did something else that matters enormously for our story. He carefully distinguished between magnetism and that amber rubbing effect. He showed that lots of materials, not just amber, could be rubbed to attract light objects: glass, sulfur, sealing wax, gemstones, all sorts of things. And he coined a word for this property. He called it the electric force, from the Latin electricus, which came from the Greek electron. Amber. That word, born from tree resin, fossilized millions of years ago, rubbed on a Greek philosopher's cloak. That's where we get electricity, electric, electron, electronics, everything. The whole vocabulary of the modern world traces back to a golden stone. Now, Gilbert didn't understand what the electric force actually was. He thought rubbing released some kind of material effluvia, a thin, invisible vapor that flowed out of the rubbed object and pulled things toward it. He was wrong about the mechanism, but he was right that this was a distinct phenomenon worth studying on its own terms, separate from magnetism. And that distinction, that simple act of saying this is its own thing, let's give it its own name and investigate it properly, opened the door. After Gilbert, things started to pick up. Through the 1600s and into the 1700s, natural philosophers across Europe began playing with static electricity more seriously. They built machines to generate it, early electrostatic generators that used spinning glass globes rubbed against pads to build up charge. One of the most important was invented by Otto von Guericke in the 1660s. Von Guericke is better known for his vacuum experiments. He's the guy who famously showed that two teams of horses couldn't pull apart two bronze hemispheres with the air pumped out. But he also built a sulfur globe that, when spun and rubbed, could attract and repel small objects, produce sparks, and even make a faint glow in the dark. He was generating static, electricity on a scale no one had before, and the sparks and the glow hinted at something deeper, something energetic, happening inside the material. And this is where it starts to get really interesting, because by the early 1700s, people were generating enough static charge to start noticing its behaviors more carefully. They noticed that charge could be transferred from one object to another. They noticed that some materials carried charge easily: metals, water, the human body, while others didn't. Glass, silk, dry wood. The ones that carried charge easily would later be called conductors. The ones that didn't would be called insulators. But at the time, the terminology was different. The English electrician Stephen Gray, working in the 1720s and 1730s, was one of the first to really nail down this distinction. Gray did these wonderful, slightly mad experiments where he'd charge a glass tube by rubbing it, then touch it to a long piece of pack thread, just ordinary, string, and show that the electric virtue, as he called it, could travel along the string over enormous distances. He transmitted charge along threads hundreds of feet long, strung across his garden and suspended from silk loops. Silk, because silk didn't let the charge leak away. If he used metal wire to suspend the thread, the charge drained off. If he used silk, it stayed. Gray had discovered electrical conduction and insulation through pure experiment, just by trying things and paying attention. Think about what that means. Before Gray, people thought the electric force was a property of certain special materials: amber, glass, sulfur. After Gray, it became clear that electricity was something that could move. It wasn't locked inside the amber. It could flow from one place to another through the right materials if you gave it a path. That's a huge conceptual shift. Electricity went from being a static curiosity to being something dynamic, something that traveled, And once you realize something can flow, you start thinking about it very differently. You start thinking about where it comes from, where it goes, what carries it, what stops it. You start thinking about it almost like a fluid. And that's exactly what people did. In the mid-1700s, the dominant theory was that electricity was literally a fluid, or maybe two fluids. The one fluid theory was championed by none other than Benjamin Franklin. Yes, that Benjamin Franklin, the one with the kite. We'll get to the kite. But first, let's talk about what Franklin actually contributed to electrical theory, because it's much more than most people realize. Franklin was in his 40s when he got interested in electricity, already a successful printer and civic leader in Philadelphia. In 1743, he attended a demonstration of electrical tricks by a traveling lecturer, and it captivated him. He started experimenting obsessively, ordering equipment from London, recruiting friends, spending hours in his workshop. And within a few years, he'd made several genuinely important contributions. First, Franklin proposed that electricity was a single fluid present in all matter. When you rubbed amber on fur, you weren't creating electricity, you were transferring it. The amber gained extra fluid, and the fur lost some. He called the condition of having extra fluid positive and the condition of having a deficit negative. Those terms, positive and negative, are still what we use today. Every time you see a plus or minus sign on a battery, that's Franklin's convention from the 1740s. Now, it turns out, Franklin guessed wrong about which direction the fluid actually moved. He thought it flowed from positive to negative, but when electrons were discovered about 150 years later, it turned out they flow from negative to positive. This is why, to this day, there's a confusing distinction in electrical engineering between conventional current and electron flow. Conventional current points from positive to negative, because that's what Franklin said. Electron flow goes the other way. It's a historical accident that still trips up students, and it's all because a printer in Philadelphia had a 50-50 chance and picked the wrong direction. But his framework, the idea that charge is conserved, that it's not created or destroyed but just moved around, that was exactly right, and it's one of the most fundamental principles in all of physics. And then there's the kite. June 1752, or thereabouts. The exact date is actually a little uncertain. Franklin wanted to prove that lightning was electrical in nature, the same stuff he'd been playing with in his workshop, just on a vastly larger scale. The idea wasn't entirely his. Others had speculated about it. But Franklin designed an experiment, and as far as we know, actually did it. He flew a kite into a thunderstorm with a metal key attached to the string near his hand, and a silk ribbon between the key and his knuckles for insulation. When the storm charged the wet string, he brought his knuckle close to the key and drew a spark. He also collected charge in a device called a Leyden jar, which was basically the earliest form of a capacitor, a glass jar coated inside and out with metal foil that could store static charge. Here's the thing about this experiment that doesn't get talked about enough. It was extraordinarily dangerous. A few months later, a Swedish physicist named Georg Wilhelm Richmann tried a similar experiment in St. Petersburg and was killed instantly by a direct lightning strike to his equipment. Killed. Dead on the floor of his laboratory. Franklin was lucky. If the kite had taken a direct strike, rather than just picking up ambient charge from the electrified air, he almost certainly would have died too. And the history of electricity, and of America for that matter, would have been very different. But Franklin survived, and the experiment proved the point. Lightning was electricity. The same force that made amber grab feathers was the same force that split trees and set buildings on fire. And that realization led directly to something practical: the lightning rod. Franklin proposed that a pointed metal rod mounted on top of a building and connected to the ground by a wire would silently draw off the charge and protect the structure. It worked. It was one of the first real practical applications of electrical science, and it saved countless buildings and lives. Churches, which were often the tallest structures in a town, and therefore the most frequent lightning targets, were among the first to adopt them, though not without controversy. Some clergy argued that diverting God's lightning was presumptuous. Franklin, diplomatically, suggested that it was no more presumptuous than putting a roof on your house to divert God's rain. So by the mid-1700s, here's where we stood. People knew that electricity was real, that it could be generated by friction, that it could flow through conductors and be blocked by insulators, that it came in two varieties, positive and negative, that it could be stored in Leyden jars, and that lightning was a natural form of it. That's a remarkable amount of progress from rubbing amber on fur. But notice what's missing. Everything so far was static electricity, charge that was built up and discharged in a single spark or slowly leaked away. Nobody had figured out how to make electricity flow continuously, steadily, in a sustained current. And without that, electricity was still basically a toy. Impressive, sometimes dangerous, scientifically fascinating, but not useful in any sustained, practical way. The thing that changed everything, the invention that turned electricity from a curiosity into a force that would reshape civilization, came from an unexpected place. It came from a dead frog's leg twitching on an Italian anatomist's table. And the man who noticed it had no idea what he'd actually stumbled onto. Luigi Galvani was a professor of anatomy at the University of Bologna, and sometime around 1780, he was doing what anatomists did, dissecting frogs. The story goes that a metal scalpel touched an exposed nerve in a frog's leg while a nearby electrostatic machine happened to spark, and the leg kicked, just twitched, right there on the table. A dead frog, no life left in it, and yet the leg moved as if it were alive. Now Galvani was a careful scientist, and he didn't just shrug this off. He started experimenting deliberately. He found that if he touched two different metals to the nerve and muscle of a frog's leg, say a copper hook and an iron plate, the leg would contract every time. No electrostatic machine needed, no Leyden jar, just two metals and dead tissue, and you'd get this eerie little kick of motion. Galvani published his findings in 1791, and his explanation was that the frog itself was the source of the electricity. He called it animal electricity. He believed that living tissue, or recently living tissue, contained some kind of inherent electrical fluid, and that the metals were just completing a circuit that allowed this biological electricity to discharge through the nerve and cause the muscle to contract. It was a beautiful, intuitive theory, and it captured the imagination of the age. The idea that life itself was somehow electrical felt profound. It felt like you were touching the very mechanism of what made living things alive. And honestly, Galvani wasn't entirely wrong. There really is electrical activity in living tissue, in your nerves, in your brain, right now as you're listening to this. But he was wrong about what was happening in his specific experiment, and the person who figured out the real explanation was a friend of his who became, in the way these things sometimes go, a rival. Alessandro Volta was a physicist at the University of Pavia, about 200 kilometers northwest of Bologna. He read Galvani's paper and was initially impressed, but the more he thought about it, the more something nagged at him. Volta noticed that the key ingredient in Galvani's experiments wasn't the frog. It was the two different metals. When Galvani used the same metal for both contacts, nothing happened. The twitch only occurred when two dissimilar metals were involved, and that suggested to Volta that the electricity wasn't coming from the animal tissue at all. The frog's leg was just acting as a detector, a very sensitive one, sure, but the actual source of the electricity was the contact between two different metals, with some moist substance between them. This led to one of the great scientific arguments of the 1790s. Galvani and Volta went back and forth, each running experiments to support their side, each publishing papers, each gathering followers. It was genuinely heated. Galvani's supporters called themselves the animalists. Volta's called themselves the metallists. And here's the thing. Volta was right about the immediate question. The electricity in those experiments really was being generated by the bimetallic contact. But to prove it conclusively, he needed to show that you could generate electricity with metals and a moist conductor without any animal tissue at all. So around 1799, Volta did something brilliant. He took small discs of copper and zinc, two different metals, and stacked them in alternating layers with pieces of cardboard or cloth soaked in salt water between each pair. Copper, wet cardboard, zinc. Copper, wet cardboard, zinc. Over and over, stacked into a column. And when he connected a wire from the bottom of the stack to the top, electricity flowed. Not a spark, not a single jolt, a continuous, steady current. For the first time in human history, someone had created a reliable, sustained source of electric current. He announced his invention in a letter to the Royal Society of London in March of 1800, and it became known as the voltaic pile. And I want you to think about what this meant, because it really was a before and after moment. Before the voltaic pile, every electrical experiment depended on static charge. You'd rub something, or you'd charge up a Leyden jar, and you'd get a brief discharge, a spark, a shock, a single dramatic moment, and then it was over. You had to start again. The voltaic pile changed that completely. Now you could have electricity flowing through a wire for minutes, hours even, as long as the chemicals held out. It was like the difference between a camera flash and a lamp. One gives you a single instant of light. The other lets you actually see by it. And the name stuck, by the way. We measure electrical potential in volts, named after Alessandro Volta. When you see a 9-volt battery or a 240-volt outlet, that's his legacy right there. Every time you check the voltage on anything, you're quietly honoring an Italian physicist who stacked metal discs and wet cardboard in his laboratory in Pavia. Now, let's talk about what's actually happening inside a voltaic pile, because this is where chemistry and electricity meet, and it's genuinely elegant. When you put zinc in contact with a saltwater solution, the zinc atoms have a tendency to dissolve, to give up electrons, and become positively charged ions that drift into the solution. Those freed electrons want to go somewhere. The copper, on the other hand, doesn't dissolve as readily. So if you connect the zinc to the copper through an external wire, those electrons have a path. They flow from the zinc, through the wire, to the copper. That flow of electrons through the wire is electric current. The chemical reaction at the zinc is literally pushing electrons out, and the copper side is accepting them. And as long as there's zinc left to dissolve and salt water to facilitate the reaction, the current keeps flowing. This is essentially how every chemical battery works to this day. Your phone battery, the battery in your car's key fob, the big lithium-ion pack in an electric vehicle. They're all descendants of Volta's pile. The materials have changed enormously. The chemistry has gotten far more sophisticated, but the fundamental principle is the same. Two different materials with different electrochemical potentials, separated by something that lets ions move between them, and an external circuit for the electrons to travel through. That's it. That's a battery. And here's what's really clever about stacking them. Each individual cell, one copper disk, one zinc disk, one wet separator, produces a pretty small voltage, maybe a bit under 1 volt. But when you stack them in series, the voltages add up. 10 cells give you roughly 10 volts. 20 cells, 20 volts. Volta figured this out empirically, just by stacking more and more disks and noticing that the shocks got stronger. He was essentially building the first series circuit without having the vocabulary for it. The voltaic pile spread across Europe with remarkable speed. Within weeks of Volta's letter being read at the Royal Society, scientists in England were building their own piles and running experiments, and the very first thing they discovered was astonishing. In the spring of 1800, just weeks after learning of Volta's invention, 2 English chemists named William Nicholson and Anthony Carlisle built their own voltaic pile and connected its wires to a container of water, and the water began to decompose. Bubbles appeared at each wire, oxygen at one, hydrogen at the other. They had split water into its constituent elements using electricity. This was electrolysis, and it was a revelation. It meant that electricity wasn't just a physical force. It was intimately connected to the chemical bonds that held matter together. That was a staggering insight for 1800. Humphrey Davy, working at the Royal Institution in London, took this idea and ran with it. Davy was one of those figures who seems almost unfairly talented, charismatic, brilliant, a genuinely gifted public lecturer who could fill auditoriums. He built enormous voltaic piles, some with hundreds of cells, and used the powerful currents they produced to tear apart chemical compounds that had resisted every other method of analysis. In 1807 and 1808, Davy isolated a string of new elements: potassium, sodium, calcium, barium, strontium, magnesium, all by passing electric current through their molten compounds. He literally discovered new building blocks of the universe by plugging them into a battery. When he first isolated potassium, witnesses said he danced around the laboratory in delight. Tiny globules of a silvery metal that burst into flame when they touched water. Nothing like that had ever been seen before. But Davy did something else that matters even more for our story, though he didn't realize it at the time. He hired an assistant, a young man named Michael Faraday, the son of a blacksmith with almost no formal education, who had taught himself science by reading books while working as a bookbinder's apprentice. Faraday attended one of Davy's public lectures, took meticulous notes, bound them beautifully, because of course he knew how to bind books, and sent them to Davy with a letter asking for a job. Davy was impressed enough to take him on, first as a laboratory assistant, essentially a bottle washer and note-taker. But Faraday was something special. He had an intuitive grasp of physical phenomena that was almost uncanny, and over the coming decades, he would make discoveries about electricity and magnetism that would fundamentally reshape our understanding of the physical world. We'll come back to Faraday. We have to, because his story is one of the most important in all of science. But first, there's another thread we need to pick up, because while Volta and Davy were exploring what electricity could do to chemistry, someone else was about to discover a connection that would prove even more consequential: the link between electricity and magnetism. And that discovery happened almost by accident during a lecture in front of a room full of students when a Danish professor noticed something that nobody had ever noticed before. His name was Hans Christian Ørsted, and in the spring of 1820, he was giving a lecture on electricity and heat to a group of students at the University of Copenhagen. He had a voltaic battery set up, connected by a wire, and nearby on the table, almost as an afterthought, there was a compass. A simple magnetic compass, the kind sailors had been using for centuries. And when Ørsted closed the circuit, when current started flowing through the wire, the compass needle moved. It twitched. It deflected away from magnetic north and pointed toward the wire instead. Now, here's what makes this moment so remarkable. People had been wondering about a possible connection between electricity and magnetism for a long time. Lightning sometimes magnetized iron objects. Sailors occasionally reported their compasses going haywire during electrical storms. There were hints, whispers, suspicions, but nobody had ever demonstrated a clear, repeatable link, and Ørsted almost missed it. The deflection was small. The needle didn't swing dramatically. It just shifted a few degrees. Some accounts say he noticed it during the lecture itself. Others say he'd been tinkering beforehand, and the lecture was where he confirmed it. The exact details are a little fuzzy, but what matters is that Ørsted did something crucial. He didn't dismiss it. He didn't say, that's odd, and move on. He spent the next several months carefully experimenting, varying the setup, confirming and reconfirming what he'd seen. And in July of 1820, he published a short paper, written in Latin, as was still common for scientific announcements, describing his discovery. Electric current produces a magnetic effect. A wire-carrying current deflects a compass needle. Think about what that means. For all of human history up to that point, electricity and magnetism had been considered completely separate phenomena. Magnets were magnets. Electricity was electricity. They were as unrelated as sound and color. And suddenly, in a lecture hall in Copenhagen, a wire carrying current reaches out and pushes on a magnet. They're connected. They're aspects of the same underlying something. The news spread across Europe like wildfire, and the person who grabbed onto it fastest and hardest was a French physicist and mathematician named André-Marie Ampère. Within a week, literally within days of hearing about Ørsted's result, Ampère was conducting his own experiments in Paris. And Ampère didn't just confirm what Ørsted had found. He went further, much further. He showed that two parallel wires carrying electric current exert forces on each other. If the currents flow in the same direction, the wires attract. If the currents flow in opposite directions, the wires repel. No magnets involved at all, just current-carrying wires pushing and pulling on each other through empty space. This was wild. This meant that magnetism wasn't just connected to electricity, it was, in some deep sense, created by electricity. A moving electric charge produces a magnetic field. That's what Ampère demonstrated, and he went on to develop the mathematics to describe it precisely. His work was so foundational that the unit of electric current, the ampere, or amp, is named after him. When you look at a circuit breaker in your house and it says 15 amps or 20 amps, that's André-Marie Ampère, the man who figured out the mathematical relationship between current and magnetic force in a frenzy of brilliance in the autumn of 1820. But here's the thing. Ørsted had shown that electricity produces magnetism. The obvious next question, the question that was now hanging in the air, tantalizing everyone, was whether you could reverse it. Could magnetism produce electricity? If a current creates a magnetic field, could a magnetic field create a current? That question would take another 11 years to answer, and the person who finally cracked it was the young man we left back in Humphrey Davy's laboratory, Michael Faraday. By the early 1820s, Faraday was no longer just washing bottles. He had proven himself as an extraordinarily skilled experimenter, and he'd begun his own research. In 1821, shortly after Ørsted's discovery reached London, Faraday built a device that many people consider the first electric motor. It was beautifully simple. He took a bowl of mercury — mercury is a liquid metal, so it conducts electricity — and placed a permanent magnet upright in the center. Then he suspended a wire so that it dangled into the mercury, free to move. When he connected a battery and sent current through the wire began to rotate around the magnet, continuously, round and round, as long as the current flowed. It wasn't a practical motor. You couldn't use it to power anything, but it demonstrated the principle. Electric current in the presence of a magnetic field produces continuous mechanical motion, force, movement, the conversion of electrical energy into physical work. That's what every electric motor on Earth still does, from the tiny vibration motor in your phone to the massive motors that drive subway trains. The principle is the same one Faraday demonstrated with a wire and a bowl of mercury in 1821. But Faraday wanted the reverse. He wanted to create electricity from magnetism. And this is where his story gets almost poignant, because he tried for 10 years and kept failing. He knew the connection had to be there. The symmetry demanded it. If electricity makes magnetism, magnetism should make electricity. But every experiment he tried came up empty. He'd place a magnet near a wire and connect the wire to a galvanometer, a sensitive instrument that detects current, and nothing. No current, no deflection. He'd leave the magnet sitting next to the wire for hours, days, hoping something would happen. Nothing. The problem, and this is so elegant it gives you chills, was that Faraday was looking for the wrong thing. He was looking for a static effect. He thought that a magnet sitting near a wire should produce a steady current, the way a battery does. But that's not how it works. And the reason it's not how it works gets at something really deep about the nature of electromagnetism. It's change that matters, not the presence of a magnetic field, but the change in a magnetic field. A magnet sitting still next to a wire does absolutely nothing. But move that magnet, slide it toward the wire, or pull it away, or spin it, and suddenly, current flows. The moment you stop moving, the current stops. It's the change, the variation, the motion that generates electricity. Faraday finally figured this out on August 29, 1831. He had wound 2 separate coils of wire around an iron ring. Think of it like a donut made of iron, with wire wrapped around one side and a different wire wrapped around the other side. He connected one coil to a battery and the other coil to a galvanometer. And when he closed the switch, when current first started flowing through the first coil, the galvanometer on the second coil jumped, just for an instant, a momentary pulse of current. Then it settled back to 0, even though current was still flowing through the first coil. And when he opened the switch, when he stopped the current, the galvanometer jumped again in the opposite direction. Another momentary pulse. Do you see what was happening? The first coil, when current flowed through it, became an electromagnet. It created a magnetic field in the iron ring. And that magnetic field, passing through the second coil, did nothing as long as it was steady. But at the moment the field was building up, at the moment of change, when the switch was first closed. That changing magnetic field induced a current in the second coil. And when the field collapsed, when the switch was opened, the change in the opposite direction induced a current in the opposite direction. This is electromagnetic induction. This is the principle behind essentially all large-scale electricity generation on the planet. Every coal plant, every nuclear plant, every hydroelectric dam, every wind turbine, they all work by moving magnets relative to coils of wire, or coils of wire relative to magnets. Changing magnetic fields, creating electric current. That's it. That's the secret. When you flip a light switch in your house, the electricity flowing through that wire was almost certainly generated by electromagnetic induction, by some version of what Faraday discovered with his iron ring and 2 coils of wire on a late summer day in 1831. And Faraday didn't stop there. He quickly built the first true electric generator, a copper disc spinning between the poles of a magnet with brushes touching the edge and the center of the disc to pick up the current. It was crude, it was inefficient, but it worked. Mechanical motion in, electrical current out. The reverse of his 1821 motor. He'd closed the loop. Electricity makes magnetism makes motion. Motion in magnetism makes electricity. Energy flows back and forth between these forms, conserved, convertible, endlessly useful. Now here's something about Faraday that makes his achievements even more extraordinary. He had almost no mathematics. He never learned calculus. He couldn't write an equation to save his life. And yet he understood electromagnetism more deeply and more intuitively than almost anyone alive. He thought in pictures. He imagined invisible lines of force spreading out from magnets and charges, curving through space, filling the room, around them. He called them lines of force, and he could practically see them. When iron filings arrange themselves in those beautiful curved patterns around a magnet, you've probably seen pictures of that. Those patterns are what Faraday was imagining in his mind's eye all the time. The mathematical physicists of his era were a bit snobbish about this. They preferred action at a distance, the idea that forces just reach across empty space instantaneously, without anything in between. Faraday's lines of force, his insistence that something real existed in the space around magnets and charges, seemed vague and unrigorous to them. They were wrong, and Faraday was right. But it would take another genius to prove it. That genius was James Clerk Maxwell, a Scottish physicist born in 1831, the very year Faraday discovered induction. Maxwell was everything Faraday wasn't, mathematically speaking. He was a prodigy, educated at Edinburgh and Cambridge, fluent in the most advanced mathematics of his time. And he was also deeply generous and intellectually humble. He recognized that Faraday's physical intuition was extraordinary, and he set himself the task of translating Faraday's visual, intuitive ideas into precise mathematical language. What Maxwell produced over a period of about a decade from the mid-1850s to the mid-1860s was one of the greatest intellectual achievements in human history. He wrote down 4 equations, just 4, that describe the complete behavior of electric and magnetic fields. Everything. How charges create electric fields, how currents create magnetic fields, how changing magnetic fields create electric fields, which is Faraday's induction, and how changing electric fields create magnetic fields, which was Maxwell's own addition, his stroke of genius that completed the symmetry. Those 4 equations, known as Maxwell's equations, are carved into the foundation of modern physics. They're beautiful in the way that only deep truths can be beautiful, compact, symmetric, and far more powerful than they look. And when Maxwell worked through the math, when he combined his 4 equations and solved them together, something astonishing fell out. The equations predicted the existence of waves, oscillating electric and magnetic fields, leapfrogging through space, each one generating the other, propagating outward at a specific speed. Maxwell calculated that speed, and it was the speed of light. Let that sink in for a moment. Maxwell sat down with equations describing batteries and magnets and compass needles and coils of wire, and out of those equations came the speed of light. Light itself, the thing that lets you see, the thing that crosses 93 million miles from the sun to warm your face, turned out to be an electromagnetic wave. An oscillation of the same fields that Ørsted had noticed twitching a compass needle in Copenhagen that Faraday had used to generate current from a spinning disk. Light, radio waves, X-rays, the microwaves that heat your food, the infrared radiation your TV remote uses, all the same thing. Electromagnetic waves, differing only in frequency and wavelength, all predicted by Maxwell's 4 equations. Maxwell published his complete theory in 1865 in a paper called A Dynamical Theory of the Electromagnetic Field. He was 34 years old. And here's the bittersweet part. He died in 1879 at just 48 of stomach cancer. He didn't live to see the experimental confirmation of electromagnetic waves. That confirmation came in 1887 when a German physicist named Heinrich Hertz built an apparatus that could generate and detect radio waves across a room. Hertz showed that these waves reflected, refracted, and interfered just like light, exactly as Maxwell had predicted. When someone asked Hertz what the practical applications of his discovery might be, he reportedly said something like, "It's of no use whatsoever." He saw it as pure physics, a beautiful confirmation of Maxwell's theory. Nothing more. He could not have been more wrong. Within a decade, Guglielmo Marconi would be sending radio signals across the Atlantic. But that's a story about communication, and our story is about something a little different, about how electricity went from a laboratory curiosity to the thing that powers civilization. And for that, we need to go back to the practical side of things, because while Maxwell was writing his equations and Hertz was generating radio waves, other people were asking a much more immediate question. How do you actually use electricity to do useful work on a large scale? How do you light a city? How do you run a factory? And the answers to those questions would come from a rivalry so fierce, so personal, and so consequential that people still argue about it today. The war between two systems, two visions of how electricity should be delivered to the world. On one side, Thomas Edison, the most famous inventor alive, backed by enormous wealth and absolute certainty that he was right. On the other side, a brilliant, eccentric Serbian immigrant named Nikola Tesla, and the industrialist who believed in him, George Westinghouse, a man who had already made a fortune in railroads, specifically from his invention of the air brake, and who understood something fundamental about building large systems. You needed to think about scale from the very beginning. Westinghouse wasn't just a businessman. He was an engineer himself, a tinkerer, someone who understood machinery in his bones. And when he looked at what Tesla was proposing, a complete system for generating, transmitting, and using alternating current, he saw the future. But let's back up a little, because to understand why this fight mattered so much, you need to understand what Edison had already built and why he was so convinced he was right. By the early 1880s, Thomas Edison had done something genuinely remarkable. He hadn't just invented the practical incandescent light bulb, though that alone would have been enough to make him famous. He had designed an entire system. Think about that for a second. Edison understood that a light bulb by itself was useless. You needed a way to generate the electricity, a way to distribute it through wires, switches to control it, meters to measure how much each customer used so you could charge them for it, fuses to keep things safe. He thought about all of it, every piece, down to the insulation on the wires and the design of the junction boxes. And on September 4th, 1882, he threw the switch at the Pearl Street station in Lower Manhattan and lit up about 1 square mile of New York City, 85 customers, 400 lamps. It doesn't sound like much now, but it was a revolution. For the first time, you could flip a switch and have clean, steady light. No gas, no flame, no soot, no danger of fire in quite the same way. People were astonished, and Edison's system ran on direct current. DC, the kind of electricity you get from a battery, current flowing in one direction, steady and constant. It made sense. Batteries produced DC. His generators produced DC. His light bulbs ran on DC. Everything was simple, straightforward, and it worked. Edison was a practical man above all else, and he had a deep distrust of anything he considered unnecessarily complicated. Here's the problem, though, and it's a problem that comes down to physics, to the actual behavior of electricity in wires, and it's worth understanding because it explains everything that happened next. When you push electric current through a wire, some of the electrical energy gets lost as heat. You've felt this. Phone chargers getting warm, extension cords that are slightly hot to the touch. That's electrical resistance converting energy into heat, and it's unavoidable. Now, here's the crucial part. The amount of power you lose depends on the current, the actual flow of charges through the wire. Specifically, the power lost as heat is proportional to the square of the current. Double the current, and you don't lose twice as much power. You lose 4 times as much. Triple the current, 9 times the loss. It's a brutal relationship. So if you want to deliver a lot of electrical power over a long distance without losing most of it as heat in the wires, you need to keep the current low. But power is current multiplied by voltage. That's just the definition. Power equals current times voltage. So if you want to deliver the same amount of power with less current, you need to increase the voltage. It's like water in a pipe. You can deliver a lot of water by using a fat pipe with a gentle pressure. That's high current, low voltage. Or you can use a thin pipe with enormous pressure. That's low current, high voltage. Same amount of water gets delivered either way, but the thin, high-pressure pipe loses a lot less energy to friction along the way. This is why high-voltage transmission is so important. And this is exactly where Edison's system hit a wall. His Pearl Street station operated at about 110 volts. At that voltage, to deliver meaningful amounts of power, you needed a lot of current, which meant a lot of energy lost as heat in the wires, which meant you couldn't send the electricity very far. Edison's customers had to be within about a mile of the generating station, maybe 1.5 miles if you used really thick, expensive copper cables. Beyond that, the losses were just too great. So if you wanted to electrify a whole city, you'd need a generating station every mile or so. In a dense city like New York, that was expensive, but maybe feasible. For smaller towns, suburbs, rural areas, forget it. The economics just didn't work. Now, you might be thinking, okay, so just generate the electricity at a higher voltage. And that's a fine idea. But Edison's light bulbs and motors ran on low voltage. You can't run 110-volt light bulbs on 10,000 volts. You'd need some way to step the voltage up for transmission, and then step it back down for use. And here's the thing. With direct current, there was no easy way to do that. No efficient, practical device existed in the 1880s that could take DC at one voltage and convert it to DC at another voltage without enormous losses. It's actually a surprisingly hard problem with direct current. Today we have electronic DC-DC converters, but those rely on semiconductor technology that wouldn't exist for another 70 years. Alternating current, though, alternating current is different. And this is where it gets beautiful. With AC, the current doesn't flow in one direction. It oscillates back and forth, switching direction many times per second, 60 times per second in the United States today, 50 in most of Europe. And this oscillation, this constant reversal, is what makes a simple, elegant, almost magical device possible. The transformer. A transformer is just two coils of wire wrapped around a shared iron core. That's it. No moving parts, nothing to wear out. You run alternating current through one coil and the constantly changing magnetic field. Remember Faraday's discovery that changing magnetic fields create electric current, induces a current in the second coil. And here's the clever part. The ratio of the voltages in the two coils depends on the ratio of the number of turns of wire. If the first coil has 100 turns and the second has 10,000 turns, the voltage in the second coil is 100 times higher than in the first. You've stepped it up, and you can do the reverse just as easily. Step it down for delivery to homes and businesses. This is what Tesla and Westinghouse understood. You could generate AC at a moderate voltage, step it up to tens of thousands of volts for long-distance transmission, keeping the current low and the losses tiny, then step it back down at the other end. One generating station could serve customers 50 miles away, 100 miles away, eventually hundreds of miles away. The economics were completely different. The geography was completely different. Everything changed. But Edison didn't see it that way. Or maybe he did see it, and that's what scared him. Because Edison had invested everything, his money, his reputation, his ego, in direct current. He had patents, he had infrastructure, he had paying customers, and he fought back hard. What followed was the war of currents, and it got ugly. Edison launched a public relations campaign against alternating current, and his central argument was that AC was dangerous. High-voltage AC could kill you, and he wasn't wrong about that. It absolutely could. But his methods of making this argument were, well, let's just say they were ethically questionable. Edison's associates, and there's some debate about how directly Edison himself was involved, began publicly electrocuting animals with alternating current to demonstrate its dangers. Dogs, calves, and in one particularly grim public spectacle in 1903, a circus elephant named Topsy at Coney Island, though that event actually happened years after the main current war had been settled and Edison's direct involvement is disputed. The more clearly documented demonstrations happened in the late 1880s and were explicitly part of the anti-AC campaign. Edison also quietly supported the development of the electric chair as a method of execution specifically designed to use alternating current, Westinghouse's current. The idea was that if the public associated AC with death, with execution, they'd never want it in their homes. Westinghouse was furious. He reportedly said that they could have done it better with an axe. The first execution by electric chair took place on August 6, 1890, at Auburn Prison in New York. The condemned man was William Kemmler, convicted of murder, and it went badly. The first jolt didn't kill him, and the process had to be repeated. It was gruesome, and it made headlines for all the wrong reasons. But despite the horror of that event, and despite Edison's campaign, the technical advantages of AC were just too overwhelming. The turning point came in 1893 at the World's Columbian Exposition in Chicago, the Great World's Fair. Westinghouse won the contract to light the entire fair using alternating current, underbidding Edison's General Electric by a huge margin. And the result was spectacular. The fairgrounds were illuminated by over 100,000 incandescent lamps, and the sight of all that electric light, the White City, they called it, was genuinely awe-inspiring for the millions of people who visited. Many of them had never seen electric light at all. For them, this was the future made visible. And then came the project that sealed it. Niagara Falls. People had dreamed for decades about harnessing the power of that enormous waterfall. And in 1893, the Niagara Falls Power Company awarded the contract to build the generating station to Westinghouse using Tesla's polyphase AC system. The first power reached Buffalo, New York, 26 miles away, on November 16, 1896. 26 miles. Edison's DC system could barely manage one. That distance was the argument, made physical, made undeniable. Tesla's AC system had won. And the principles behind it, generate at moderate voltage, step up for transmission, step down for delivery, are exactly the same principles that power grids use today, all over the world. Every time you plug something into a wall outlet, you're using the system that Tesla envisioned and Westinghouse built. But here's what's interesting about Tesla himself, and it's worth pausing on, because his story is one of the strangest in all of engineering history. Nikola Tesla was born in 1856 in Smiljan, in what is now Croatia, but was then part of the Austrian Empire. His father was a Serbian Orthodox priest. As a young man, Tesla had an almost supernatural ability to visualize machines in his mind. He claimed he could build an entire device mentally, test it, even see where the parts would wear, all without drawing a single diagram. He studied engineering in Graz, Austria, and it was there, as a student, that he first became obsessed with the idea of an AC motor that didn't need the sparking, unreliable commutator that DC motors required. The solution came to him in 1882, while walking in a park in Budapest. He was reciting poetry, Goethe's Faust, of all things, when the concept of the rotating magnetic field flashed into his mind, fully formed. He sketched it in the dirt with a stick. The idea was that if you used multiple phases of alternating current, offset in time from each other, you could create a magnetic field that rotated smoothly inside the motor, dragging the rotor along with it. No brushes, no commutator, no sparking. Simple, elegant, and incredibly robust. He arrived in New York in 1884 with 4 cents in his pocket, a book of poetry, and a head full of ideas that would reshape the world. He worked briefly for Edison, and the two men could hardly have been more different. Edison was relentless, empirical, a brute force experimenter who famously said that genius was 1% inspiration and 99% perspiration. Tesla was intuitive, theoretical, a man who worked things out in his mind before ever touching a piece of metal. They clashed, and Tesla left after just a few months, reportedly over a dispute about money. Edison may have promised him a bonus and then reneged, though the details are murky. After a rough period that included digging ditches to survive, Tesla found backers, set up his own laboratory, and in 1888 delivered a landmark lecture to the American Institute of Electrical Engineers, demonstrating his polyphase AC system. Westinghouse was in the audience, or at least heard about it, immediately, and within weeks He had licensed Tesla's patents for $60,000 plus royalties, a fortune at the time. And that partnership, that combination of Tesla's vision and Westinghouse's industrial muscle, is what made everything possible. But Tesla's later years were difficult. And this is the bittersweet part. He gave up his royalty agreement with Westinghouse when the company was in financial trouble. A decision that cost him what would have been millions, possibly hundreds of millions of dollars. He spent decades pursuing increasingly grandiose ideas, some brilliant, some impractical: wireless power transmission, death rays, earthquake machines. He grew eccentric, living alone in hotels, feeding pigeons in the park, claiming to have fallen in love with a particular white pigeon. He died on January 7th, 1943, in a room at the New Yorker Hotel, alone and largely forgotten by the public, though his contributions to electrical engineering were immense. So, the AC system won, and now the question became something even bigger: not just how to deliver electricity to one city or one factory, but how to build a network, a grid, that could connect generators to consumers across an entire country. And this is where the story shifts from individual inventors to something more like a collective engineering project, because building the electrical grid turned out to be one of the most complex infrastructure challenges in human history, because you're not just stringing wire from point A to point B. You're building a living, breathing system that has to balance supply and demand in real time, every single second of every single day. And if it gets out of balance even a little, things start to go very wrong very fast. Let's talk about why that is, because it's one of those things that seems simple on the surface but gets incredibly deep once you start pulling at it. Electricity, unlike almost every other commodity we use, can't really be stored. Not in any practical, large-scale way, at least not for most of the 20th century. And even now, storage remains one of the great unsolved challenges. Think about that. Water, you can put in a reservoir. Oil, you can put in a tank. Grain, you can put in a silo. But electricity, the moment it's generated, it has to be consumed. If you produce more than people are using, the excess energy has to go somewhere, and what happens is the generator starts spinning faster. The frequency of the AC current rises above its target. 60 hertz in North America, 50 hertz in most of the rest of the world, and equipment starts misbehaving. If you produce less than people are demanding, the generators slow down, the frequency drops, and eventually things start shutting off. Or, worse, the whole system can cascade into a blackout. So the grid is this constant, delicate balancing act. Every time someone flips on a light switch, somewhere a generator has to produce just a tiny bit more power. Every time a factory shuts down for the night, generation has to be dialed back. And all of this has to happen more or less instantaneously. Now, in the very early days, this wasn't such a huge problem, because the grids were small and isolated. Edison's Pearl Street station served a few blocks of Lower Manhattan. Westinghouse's early AC systems might serve a single town. Each little system had its own generator, its own customers, and the operator could more or less keep an eye on things directly. But as demand grew, and it grew explosively, because once people had electric light, they wanted electric everything, these isolated systems started bumping into each other, and engineers realized that connecting them together would make the whole thing more reliable and more efficient. Here's the logic. If you have two separate power stations, each one has to have enough capacity to handle its peak demand all by itself, plus some extra margin for safety. But peak demand doesn't happen at the same time everywhere. A residential neighborhood uses the most power in the evening, when everyone's home cooking dinner and turning on lights. A factory district uses the most during the day shift, If you connect those two systems together, the total generating capacity you need is less than the sum of what each one would need separately, because their peaks don't overlap perfectly. This is called load diversity, and it's one of the fundamental economic arguments for building an interconnected grid. You share resources, you share risk, and everybody benefits. But connecting systems together introduces a whole new set of problems. And this is where the engineering gets really fascinating. Remember, AC power has a frequency, 60 cycles per second in the US, and when you connect two generators to the same grid, they have to be synchronized. They have to be spinning at exactly the same speed, and their voltage waveforms have to be in phase with each other. If you try to connect a generator that's slightly out of sync, the results can be violent. Massive currents can flow between the machines, shafts can twist, windings can burn out. Early grid operators learned this the hard way. Synchronizing generators became one of the essential skills of power system operation, and specialized instruments called synchroscopes were developed to help operators match the frequency, voltage, and phase angle of a generator to the existing grid before closing the connection. And as grids grew larger through the early 1900s, the challenge of keeping everything synchronized across longer and longer distances became more and more complex. The man who probably did more than anyone to think systematically about this was Samuel Insull, and he's a figure worth spending some time on, because his story is both inspiring and cautionary in equal measure. Insull was born in London in 1859, and as a young man he became Thomas Edison's personal secretary. Traveled to America in 1881 specifically to work for Edison, and quickly proved himself indispensable. He was brilliant with both technology and business, which is a rare combination. After Edison's various companies were consolidated into General Electric in 1892, Insull moved to Chicago to run a small utility called Chicago Edison. And what he did there over the next 3 decades essentially invented the modern electric utility. Insull understood the load diversity principle intuitively. He aggressively sought out different types of customers, not just wealthy homes and offices, but factories, streetcar lines, department stores, specifically because their usage patterns were different, and mixing them together flattened the overall demand curve, which meant his generators could run more efficiently. He pioneered the concept of the demand charge, where large customers paid not just for the energy they used, but for the peak capacity they required. He drove down the cost of electricity relentlessly, and as prices fell, demand surged, which justified building bigger and more efficient power plants, which drove prices down further. It was a virtuous cycle, and Chicago became one of the best electrified cities in the world. But here's where it gets complicated. Insull also built an enormous financial empire, a pyramid of holding companies that owned other holding companies that owned the actual utilities. It was leveraged to an extraordinary degree, and for a while, during the Roaring '20s, it seemed like genius. The stock prices kept climbing, the dividends kept flowing, and Insull was hailed as one of the great business minds of the age. Then the stock market crashed in 1929, and the whole structure came tumbling down. By 1932, Insull's companies had collapsed, wiping out the savings of hundreds of thousands of small investors who had bought stock in his utilities. He fled the country, was eventually extradited, stood trial for fraud and embezzlement, and was actually acquitted because what he'd done, while reckless, wasn't technically illegal under the laws of the time. But his reputation was destroyed, and more importantly, the collapse of his empire led directly to some of the most significant utility regulation in American history. The Public Utility Holding Company Act of 1935 broke up the giant utility pyramids and established the regulatory framework that governed American electric utilities for decades. So, Insull's legacy is this strange duality. He genuinely figured out how to make electricity cheap and widely available, and he also demonstrated exactly how badly things could go wrong when financial engineering outpaced the actual engineering. But let's come back to the physical grid itself, because while the business side was sorting itself out through booms and busts and regulation, the engineers were solving problems that were just as challenging in their own way. One of the big ones was voltage regulation over long distances. We talked earlier about how transformers let you step voltage up for transmission and back down for distribution, and that's the core insight that made AC viable. But in practice, when you're pushing power across hundreds of miles of wire, things get more complicated than just Ohm's law. Long transmission lines have inductance and capacitance. They behave a bit like antennas, actually, which makes sense when you remember that Maxwell showed us electricity and magnetism are really the same phenomenon. The inductance of a long line causes the voltage to drop under heavy load, which means the voltage at the far end of the line can be significantly lower than at the sending end. And the capacitance of the line, especially when it's lightly loaded, can actually cause the voltage at the receiving end to rise above the sending voltage, a phenomenon called the Faraday effect, named after Sebastian Ziani de Ferranti, who encountered it in the 1890s while building one of London's early power systems. He designed a transmission line from Deptford to central London, about 7 miles, operating at what was then the remarkably high voltage of 10,000 volts, and discovered that when the load was light, the voltage at the London end climbed higher than at Deptford. It was puzzling at the time, but it's a straightforward consequence of the line's distributed capacitance resonating with its inductance. Managing these voltage variations required new tools and new thinking. Engineers developed tap-changing transformers that could adjust their turns ratio while in service, compensating for voltage drops as load changed throughout the day. They added capacitor banks and inductor banks, called reactive compensation, at strategic points along transmission lines to keep the voltage stable. And they developed increasingly sophisticated ways to analyze power flow through complex networks, because once you have dozens or hundreds of generators feeding thousands of miles of interconnected lines serving millions of customers, you can't just do the math on the back of an envelope anymore. This is actually where one of the great unsung tools of electrical engineering comes in: the network analyzer. Before digital computers were available, power system engineers built elaborate analog models of their grids using miniature resistors, inductors, and capacitors wired together on large boards to represent the actual transmission lines, generators, and loads. These network analyzers, sometimes called AC calculating boards, could fill an entire room. You'd set up the model to match your grid, apply voltages representing your generators, and measure the currents and voltages at every point in the network to see how power would flow, where bottlenecks would occur, what would happen if a particular line went down. General Electric and Westinghouse both built these machines, and utilities relied on them heavily from the 1930s through the 1960s until digital computers became powerful enough to take over the calculations. And those calculations matter enormously, because the consequences of getting them wrong can be catastrophic. The most dramatic demonstration of this came on November 9, 1965, when a single relay, a protective device designed to disconnect a transmission line if the current exceeded a preset threshold, tripped on a line near Niagara Falls. The threshold had been set years earlier and never updated, even though the normal power flow on that line had gradually increased as demand grew. When the relay tripped, the power that had been flowing on that line had to redistribute itself across the remaining lines, and some of those lines became overloaded too, so their protective relays tripped, and within minutes, a cascade of failures spread across the entire northeastern United States and parts of Ontario. 30 million people lost power. It was the largest blackout in history at that point, and it lasted up to 13 hours in some areas. The 1965 blackout was a watershed moment. It revealed just how interdependent the grid had become, and how a single point of failure could propagate across an enormous area if the system wasn't designed to contain such cascades. In response, the electric utility industry created what eventually became the North American Electric Reliability Corporation, NERC, to develop and enforce reliability standards across the interconnected grid. And engineers began developing more sophisticated approaches to what's called contingency analysis, essentially asking, over and over, what happens if this particular component fails, and making sure the system can survive any single foreseeable failure without cascading. But here's what's really remarkable about the grid when you step back and think about it. Despite its complexity, despite the fact that it has to balance supply and demand instantaneously across millions of points of generation and consumption, despite the fact that it's exposed to weather, equipment failures, human error, and all manner of unpredictable events, it works. It works astonishingly well, actually. In a typical year, the average American customer experiences maybe a few hours of outage total. The lights come on when you flip the switch, something like 99.9 something% of the time, and we take that so completely for granted that we barely notice it until the rare moment when it fails, and suddenly everything stops, and you realize just how utterly dependent we are on this invisible infrastructure humming away behind the walls. The frequency of the grid, that 60 Hz in North America, 50 Hz in Europe, is actually one of the most tightly controlled quantities in all of engineering. Grid operators monitor it constantly, and deviations of even a fraction of a hertz trigger automatic responses. Generators have governors that adjust their fuel input to speed up or slow down in response to frequency changes. And the collective inertia of all those massive spinning generators acts as a buffer, a kind of flywheel effect that resists sudden changes in frequency and gives operators a few seconds to respond. It's elegant in a way. All those generators, scattered across a continent, spinning together in lockstep, connected by nothing but copper and aluminum wire, and the laws of physics that Faraday and Maxwell worked out over a century earlier. And this brings us to something that's been quietly revolutionizing the grid over the last few decades, something that would have seemed almost magical to the engineers who built those first interconnected systems: the rise of power electronics. Because for most of the 20th century, the grid was an analog system through and through. Generators spun, transformers stepped voltages up and down, switches opened and closed mechanically, and the flow of power was governed by the physical properties of the wires and machines themselves. But starting in the 1960s and accelerating dramatically from the 1980s onward, semiconductor devices began to change everything. And the key device at the heart of this revolution is something called a thyristor. Now, a thyristor is basically a semiconductor switch, a solid-state component, no moving parts, that can handle enormous amounts of electrical power. Think of it like a gate that you can open with a tiny signal, and once it's open, it lets a huge current flow through. The first practical thyristors appeared in the late 1950s, developed by engineers at General Electric. and they were a direct descendant of the transistor that Bardeen, Brattain, and Shockley had invented at Bell Labs in 1947. But while transistors were being miniaturized for radios and computers, thyristors went the other direction. They got bigger, beefier, designed to handle thousands of volts and thousands of amps. And what they allowed engineers to do was something genuinely transformative. They could now convert AC to DC and back again, at scale, with precision, and without the clunky, maintenance-heavy mechanical converters that had been used before. Now, why would you want to convert AC to DC on a power grid that's built entirely around alternating current? That's a great question, and the answer takes us back to a problem that Tesla and Westinghouse's AC system solved beautifully but not completely. Remember, AC won the war of currents because transformers made it easy to step voltage up for long-distance transmission and step it back down for local use. And that's still true. But AC has some quirks over very long distances or in certain specific situations. For one thing, AC transmission lines have what's called reactive power. The electromagnetic fields around the conductors store and release energy with every cycle 60 times a second, and that creates losses and complications that get worse the longer the line is. There's also the issue of skin effect, where alternating current tends to flow mostly near the surface of a conductor rather than using the full cross-section, which effectively increases resistance. And if you're trying to send power through an undersea cable, AC becomes really problematic because the cable's capacitance, its ability to store charge between the conductor and the surrounding water, absorbs so much reactive current that beyond a certain distance, maybe 40 or 50 miles, you're basically just charging and discharging the cable and barely any real power gets through to the other end. High voltage direct current, or HVDC, solves all of these problems. DC doesn't have reactive power losses, doesn't suffer from skin effect in the same way, and works beautifully in long submarine cables. The concept had been understood for decades, but the practical challenge was always the conversion. You need to turn AC into DC at the sending end, transmit it, and then turn it back into AC at the receiving end so it can feed into the local grid. Before thyristors, this conversion required mercury arc rectifiers, which were these enormous, finicky, expensive vacuum devices that needed constant maintenance. The first major HVDC link using mercury arc valves was a connection between the Swedish mainland and the island of Gotland in 1954, built by a company called ASEA, which would later become part of ABB. It was a 20-megawatt link, modest by today's standards, but it proved the concept worked. Then, thyristors changed the game. By the 1970s, thyristor-based HVDC converters were replacing mercury arc systems, and suddenly HVDC became practical at much larger scales. The Pacific Intertie, completed in 1970 and upgraded several times since, sends power from the hydroelectric dams of the Columbia River Basin in the Pacific Northwest all the way down to Los Angeles, about 850 miles. At its peak capacity, it can transmit over 3,000 megawatts, enough to power a couple million homes. That's a river of electrons flowing from Oregon to Southern California, converted from AC to DC, shot down a pair of high-voltage lines at something like plus and minus 500,000 volts, and then converted back to AC at the other end. And the thyristors at each converter station make it all possible, switching on and off thousands of times per second with split-second precision. Here's what's really clever about power electronics, though. It's not just about HVDC. Once you have semiconductor devices that can switch large currents on and off rapidly, you can do all sorts of things that were impossible in the old analog grid. You can build devices called FACS, flexible AC transmission system devices, that can dynamically control the flow of power on AC lines, adjust reactive power in real time, and stabilize voltages almost instantaneously. Before FACS, if you wanted to reroute power flow on the grid, your options were limited to opening and closing mechanical breakers or adjusting generator outputs, both of which are relatively slow. With FACS devices, you can fine-tune power flow the way a sound engineer adjusts levels on a mixing board. It gives grid operators a level of control that the pioneers of the interconnected grid could barely have imagined. And this matters more than ever now because of something that's fundamentally changing the nature of electricity generation: renewables. For most of the grid's history, generation came from large centralized power plants: coal, natural gas, nuclear, hydro. Big spinning machines connected to the grid, each one contributing its share of that all-important rotational inertia we talked about. Each one dispatchable, meaning operators could tell it to ramp up or ramp down as needed. But solar panels and wind turbines are different in almost every way. Solar panels produce DC, direct current, with no moving parts at all. Wind turbines spin, but at variable speeds depending on how hard the wind is blowing, which means their output frequency doesn't naturally match the grid's 60 Hz. Both solar and wind are intermittent. They produce power when the sun shines and the wind blows, not necessarily when you need it. And they're often distributed, scattered across rooftops and wind farms, rather than concentrated in a few big plants. So how do you connect these sources to a grid that was designed around big synchronous generators all spinning in lockstep? Power electronics. Every solar panel installation has an inverter, a device that converts the DC from the panels into AC at the right frequency and voltage to feed into the grid. Every modern wind turbine has a power converter that decouples the variable speed rotation of the blades from the fixed frequency of the grid. These inverters and converters are sophisticated pieces of power electronics using devices called IGBTs, insulated gate bipolar transistors, which are essentially the modern descendants of those early thyristors, but faster, more controllable, and more efficient. An IGBT can switch on and off tens of thousands of times per second, and by carefully controlling the timing of those switches, the inverter can synthesize a clean AC waveform from a DC source. It's like building a smooth wave out of tiny rectangular steps, and if you make the steps small enough and fast enough, the result is indistinguishable from the smooth sine wave that a spinning generator produces. But here's the thing, and this is one of the most pressing challenges in electrical engineering right now. When you replace spinning generators with inverter-based resources, you lose that rotational inertia. Remember, all those massive spinning turbines act as a collective flywheel, resisting sudden frequency changes and buying operators time to respond. A solar panel connected through an inverter has no inertia at all. It's just semiconductors switching. So as grids around the world add more and more renewable generation and retire conventional power plants, the total inertia of the system decreases, and the grid becomes more susceptible to rapid frequency swings. A sudden loss of a large generator or a big transmission line, which the old high-inertia grid could absorb with barely a wobble, might cause a much sharper frequency drop in a low-inertia grid, potentially triggering cascading failures. Engineers are working on this from multiple angles. One approach is synthetic inertia, sometimes called virtual inertia, where inverters are programmed to mimic the behavior of spinning machines. They monitor the grid frequency and, when they detect a drop, they momentarily boost their power output, drawing on stored energy in the DC link capacitors or briefly extracting extra energy from the wind turbine's spinning blades. It's not real inertia in the physical sense, but it provides the same stabilizing effect. Another approach is grid-scale battery storage, enormous banks of lithium-ion batteries, or increasingly other chemistries like iron-air or sodium-ion, connected to the grid through power electronics. These batteries can respond to frequency deviations in milliseconds, far faster than any mechanical governor, injecting or absorbing power almost instantaneously. The Hornsdale Power Reserve in South Australia, a 100-megawatt battery installation built by Tesla in 2017, famously demonstrated this capability, responding to a coal plant trip in the grid faster than any conventional generator could have, and saving the system from a potential blackout. And this is where the story of electricity starts to feel like it's coming full circle in a strange and beautiful way. Because remember, one of the fundamental challenges of electricity that we talked about earlier, the reason the grid has to balance supply and demand every single second, is that electricity can't be practically stored. That was true for over a century. But now, with batteries becoming cheaper and more capable every year, and with other storage technologies like pumped hydro and compressed air, and even gravity-based systems being developed, we're starting to chip away at that fundamental constraint. We're not there yet. The amount of storage on the grid today is still a tiny fraction of total generation capacity, but the trajectory is clear, and it's power electronics that makes it all possible, acting as the universal translator between DC batteries and AC grids, between variable speed wind turbines and fixed frequency transmission systems, between the old world of spinning iron and copper and the new world of silicon and lithium. There's something poetic about the fact that the semiconductor, a material that's neither a good conductor nor a good insulator, sitting right there in the ambiguous middle of the periodic table, has become the key to managing the most complex machine humanity has ever built. Silicon, germanium, gallium arsenide. These materials that Faraday himself studied back when he was experimenting with the electrical properties of different substances in the 1830s, not really understanding what he was seeing. They turned out to be the bridge between the electromagnetic principles he discovered and the modern grid that runs on them. And speaking of bridges between old and new, there's another transformation happening right now that's just as profound as the rise of power electronics, and it has to do with how we think about the grid not as a one-way street, power flowing from big plants to passive consumers, but as something far more dynamic, far more distributed, and far more intelligent. Because the grid of the 21st century is becoming something fundamentally different from what Samuel Insull or even the engineers who designed the post-war grid would have recognized. For more than 100 years, the logic was simple and unidirectional. You build a big power plant. You connect it to high-voltage transmission lines. You step the voltage down through substations, and you deliver electricity to homes and businesses that consume it. That's it. Power flows one way, from the center outward, like water from a reservoir through pipes to your faucet. The consumer at the end of the line is passive. They flip a switch, they draw power, and somewhere far away, a generator spins a little harder to meet that demand. The utility doesn't really know what's happening at the individual household level, and frankly, it doesn't need to. It knows the aggregate, the total load on a feeder, the total demand in a region, and that's enough to keep things balanced. But think about what happens when millions of those passive consumers start generating their own electricity. When a homeowner in Arizona puts solar panels on their roof, they're not just consuming power anymore. On a sunny afternoon, they might be producing more than they need, and that excess flows backward through the meter, back into the distribution network, back toward the substation. The power is flowing the wrong way. Not wrong in a moral sense, obviously, but wrong in the sense that the entire system was designed around the assumption that it would never happen. The protection relays, the voltage regulators, the tap changers we talked about earlier, all of that equipment was engineered for a world where current flows in one direction. When you suddenly reverse the flow, strange things start to happen. Voltages can rise at the end of feeders instead of dropping. Protection systems can get confused about where a fault is located. A transformer that's been happily stepping voltage down for decades is now being asked to handle power flowing backward through it. And while transformers are technically bidirectional, the physics works fine in either direction. The control systems wrapped around them weren't designed for that. This is the challenge of what's called distributed generation, and it's been growing steadily since the early 2000s. Germany was one of the first countries to really push this at scale with its Energiewende, the energy transition, which included generous feed-in tariffs that paid homeowners and farmers to install solar panels and small wind turbines. By the 2010s, Germany had tens of gigawatts of distributed solar capacity, much of it connected to low-voltage distribution networks that were originally built to serve small villages. On bright spring days, with low demand, the amount of solar power being pushed back into the grid could exceed what those local networks were designed to handle. Grid operators had to learn, quickly, how to manage a system that was behaving in ways no one had planned for. And here's where the concept of the smart grid comes in. It's one of those terms that gets thrown around a lot, sometimes vaguely, but at its core, the idea is straightforward. A smart grid is one that has sensing, communication, and control capabilities woven throughout, not just at the big power plants and major substations, but all the way down to the distribution level, even to individual homes. Instead of the utility being blind to what's happening at the edges of its network, it can see in something close to real time what's being consumed, what's being generated, where voltage is too high or too low, and where congestion is building up. And crucially, it can act on that information, automatically adjusting, rerouting, compensating. The enabling technology for a lot of this is surprisingly mundane. It starts with the smart meter. You probably have one. Most homes in the United States and Europe do now. It's that digital meter on the side of your house that replaced the old spinning disc meter a utility worker used to come read every month. A smart meter records your electricity usage in fine-grained intervals, every 15 minutes sometimes, every 5, and communicates that data back to the utility wirelessly or over the power lines themselves. That doesn't sound revolutionary, but think about what it means at scale. A utility with 5 million smart meters suddenly has 5 million data points updating every 15 minutes. That's an enormous, real-time picture of what the grid is actually doing, and it enables things that were simply impossible before. Demand response is one of the big ones. Remember how we talked about the grid needing to balance supply and demand every single second? Traditionally, the only way to do that was on the supply side. You ramp generators up and down to follow load. But what if you could also adjust the demand side? What if, on a sweltering August afternoon, when everyone's air conditioning is pushing the grid to its limits, you could send a signal to 1 million smart thermostats asking them to nudge the temperature set point up by 2 degrees for 20 minutes. Each individual household barely notices. Maybe they don't notice at all. But in aggregate, you've just shaved hundreds of megawatts off the peak demand. That's the equivalent of not having to build and run an entire peaking power plant, one of those expensive gas turbines that only operates a few hundred hours a year. This isn't hypothetical, by the way. Utilities have been running demand response programs for years. Some of them are simple. You get a discount on your bill in exchange for letting the utility cycle your water heater off during peak hours. Some are more sophisticated, using real-time pricing signals to incentivize large industrial customers to shift their energy-intensive processes to off-peak times. And increasingly, the intelligence isn't just at the utility level, but embedded in the devices themselves. Your smart thermostat, your electric vehicle charger, your home battery system. These can all be programmed to respond to grid conditions autonomously, drawing power when it's cheap and abundant, backing off when the grid is stressed. Now, let's talk about electric vehicles for a moment, because they represent both a massive challenge and a massive opportunity for the grid. A single electric car, when it's charging at home on a level 2 charger, draws about 7 to 10 kilowatts. That's roughly the same as running 2 or 3 central air conditioning units simultaneously. If you have a neighborhood where 20% of the households come home at 6 in the evening and plug in their cars, you've just added an enormous spike to the local demand right at the time when the grid is already near its daily peak. Distribution transformers that were sized for a world of gas stoves and incandescent lights could be overwhelmed. But here's the flip side, and this is what gets grid engineers genuinely excited. Those same electric vehicles are essentially batteries on wheels. A typical EV has a battery pack somewhere between 60 and 100 kilowatt hours. If you have 1 million EVs connected to the grid, and many countries are heading toward tens of millions, that's an astronomical amount of distributed storage. The concept is called vehicle-to-grid, or V2G, and the idea is that your car, when it's parked and plugged in, which is most of the time, honestly, since the average car sits idle about 95% of its life, could actually feed power back into the grid when it's needed. Your car becomes a grid asset. You drive to work, plug in, and your car's battery helps stabilize the grid during the morning demand ramp, then charges up cheaply during the midday solar surplus, then feeds power back during the evening peak. You wake up the next morning with a full battery and a credit on your electricity bill. The technical challenges are real. Battery degradation from extra cycling, the need for bidirectional chargers, complex communication protocols between the car, the charger, and the grid operator. But pilot programs are running in places like Denmark, the Netherlands, and California, and the results are promising. And the power electronics we talked about are at the heart of it, managing that bidirectional flow, converting between the DC battery and the AC grid, doing it efficiently and safely. All of this, the distributed solar, the smart meters, the demand response, the electric vehicles, the grid-scale batteries, it's converging into something that looks less like the old centralized grid and more like a network. Almost like the internet, actually. And that comparison isn't just a metaphor. The modern grid is increasingly managed by software, by algorithms, by optimization routines running in data centers that process millions of data points to make decisions about power flow in real time. Machine learning is being used to forecast solar and wind output hours or days ahead, to predict demand patterns, to detect equipment failures before they happen by analyzing sensor data from transformers and transmission lines. There's a term that power systems engineers use, the energy internet, or sometimes the Internet of Energy. And while it sounds a bit buzzwordy, it captures something real about the direction things are moving. The 20th century grid was a marvel of analog engineering, governors and voltage regulators and protection relays, all operating on local information, all designed with generous safety margins to handle uncertainty. The 21st century grid is becoming a cyber-physical system, where the physical infrastructure of generators and wires and transformers is inseparable from the digital layer of sensors, communications, and software that manages it. And that brings its own risks, of course. When you connect critical infrastructure to communication networks, you create attack surfaces that didn't exist before. Cybersecurity for the grid has become one of the most pressing concerns in the energy sector. In December 2015, hackers, widely attributed to Russian state-sponsored groups, attacked the Ukrainian power grid, remotely opening breakers at 3 distribution companies and cutting power to roughly 230,000 customers in the middle of winter. It was the first publicly confirmed cyber attack to successfully take down part of a power grid, and it was a wake-up call for utilities worldwide. The attackers didn't exploit some exotic vulnerability. They used spear phishing emails to gain access to the utilities' corporate networks, then moved laterally until they reached the industrial control systems, the SCADA systems that operated the breakers. They even jammed the utilities' phone lines to prevent customers from reporting outages, which is a chillingly methodical touch. The incident demonstrated something that grid security experts had been warning about for years, that the same connectivity that makes the smart grid possible also makes it vulnerable. And defending against these threats is fundamentally different from defending a website or a bank's database, because the consequences of a successful attack aren't financial or reputational. They're physical. People lose heat. Hospitals lose power. Traffic lights go dark. The stakes are about as high as they get. So there's this tension at the heart of the modern grid's evolution. On one side, you have the undeniable need to integrate renewables, to decarbonize, to build a more flexible and responsive system. And that requires digitization, communication, intelligence at the edge. On the other side, you have the need to keep this critical infrastructure secure and resilient, which sometimes argues for simplicity, for air gaps, for systems that fail gracefully rather than catastrophically. Navigating that tension is one of the great engineering challenges of our time, and it doesn't have a clean, simple answer. It requires layers of defense, redundancy, careful architecture, and a recognition that the grid is never finished. It's always being rebuilt, always adapting. And you know, in a way, that's been true since the very beginning. Since Edison strung those first copper mains under the streets of Lower Manhattan in 1882, the grid has been in a constant state of evolution. Every decade brought new challenges, longer distances, higher voltages, bigger loads, new sources of generation. And every decade, engineers found ways to adapt. The materials changed, from copper to aluminum, from oil paper insulation to cross-linked polyethylene. The control systems evolved, from manual switchboards to electromechanical relays to digital processors. The scale grew from a few city blocks to continental interconnections spanning thousands of miles. But the fundamental physics, Faraday's law, Ohm's law, Maxwell's equations, those haven't changed at all. They're the same equations that a student learns in their first physics class. The same relationships that Faraday intuited with his iron ring and his galvanometer nearly 2 centuries ago. And that might be the most remarkable thing about electricity as an engineering discipline. How much of the modern world rests on principles that were essentially understood by the 1860s. What's changed isn't the physics. It's our ability to manipulate it, to control it with ever greater precision, to push it through materials and devices that the 19th century pioneers couldn't have imagined. And right now, as you lie here in the quiet, the grid is doing its thing all around you. Generators spinning, electrons drifting, power electronics switching millions of times per second. algorithms optimizing flows across thousands of miles of transmission lines. All of it working together in this vast, synchronized, mostly invisible dance that keeps the lights on, keeps the air moving through your room, keeps the clock on your nightstand ticking forward one quiet second at a time. And that's really what it comes down to, isn't it? This thing we call the grid, this enormous, sprawling, impossibly complex machine, exists for moments exactly like this one. Quiet moments, ordinary moments, the hum of a refrigerator in the next room, the gentle glow of a charging indicator on your phone, the soft warmth of a heating element somewhere in the walls. None of it feels miraculous. None of it demands your attention. And that's precisely what makes it miraculous, the fact that it disappears into the background of your life so completely that you only notice it when it stops. Think about that for a second. The entire history we've wandered through tonight. Thales rubbing amber against fur and marveling at the way it pulled feathers toward it. Volta stacking zinc and copper discs into the first battery. Faraday spinning a wire around a magnet and watching it trace that strange, beautiful circle. Maxwell filling pages with equations that unified light and magnetism and electricity into a single framework. Edison laying copper under the streets of New York. Tesla dreaming of alternating current and rotating magnetic fields. Insull building the business model that electrified a nation. All those engineers synchronizing generators and balancing loads and designing thyristors and inverters and grid-scale batteries. All of that history, all of those lifetimes of work, all of those arguments and failures and breakthroughs, they all converge on this. You, lying comfortably in the dark, not thinking about electricity at all. That's the goal. That's always been the goal. To make something so reliable, so seamless, so woven into the fabric of daily life that it becomes invisible. And we're at an interesting inflection point right now, in the early decades of the 21st century, because the grid is being asked to do something it was never originally designed to do. It was built, fundamentally, as a one-way delivery system. Big power. Plants generate electricity. Transmission lines carry it long distances. Distribution networks deliver it to homes and businesses. That was the model for over a century. But now, as we talked about, the flow is becoming bidirectional. Solar panels on rooftops are pushing power back into the network. Electric vehicles parked in garages might someday feed energy back to the grid during peak demand. Wind farms in the North Sea and the Texas Panhandle are generating power that fluctuates with the weather rather than following a dispatch schedule. The grid is becoming less like a river flowing in one direction, and more like a living circulatory system, with energy flowing in multiple directions at multiple scales all at once. And the thing that makes this transition so fascinating and so difficult is that you can't just swap out the old grid for a new one. You can't shut it down for a weekend and rebuild it. The grid has to keep running while it's being transformed. Engineers sometimes compare it to rebuilding an airplane while it's in flight. And honestly, that analogy isn't much of an exaggeration. Every new solar installation, every new battery system, every new smart meter, every new high-voltage direct current link, they all have to be integrated into a system that's already operating, already balancing supply and demand 60 times a second, already keeping voltage within tight tolerances across millions of nodes. It's one of the most complex engineering challenges humanity has ever undertaken, and most people have no idea it's happening. Here's what's really interesting about where we're headed. For most of the history of electrification, the limiting factor was generation. Could you build enough power plants to meet growing demand? That was the central question for Edison, for Insull, for the engineers who built the massive coal and nuclear plants of the mid-20th century. But increasingly, the limiting factor isn't generation at all. We actually know how to generate enormous amounts of clean electricity. Solar photovoltaic costs have dropped something like 90% since 2010. Wind turbine technology has matured to the point where offshore wind farms can produce power at costs competitive with fossil fuels. The sun delivers more energy to Earth's surface in a single hour than humanity uses in an entire year. Generation isn't really the bottleneck anymore. The bottleneck is everything else. It's transmission, getting power from where it's generated to where it's needed, often across hundreds or thousands of miles, through a patchwork of regulatory jurisdictions and permitting processes that can take a decade to navigate. It's storage, figuring out how to bank energy when the sun is shining and the wind is blowing so you can use it when they're not. It's flexibility, making the grid nimble enough to handle rapid swings in both supply and demand. And it's integration, weaving all these new technologies together into a coherent system that's at least as reliable as the one it's replacing, preferably more so. Let's talk about transmission for a moment, because it's one of those things that doesn't get nearly enough attention. Building a new high-voltage transmission line in the United States today can take 7 to 12 years from proposal to completion, and most of that time isn't spent on construction. It's spent on permitting, environmental review, and negotiating with the many jurisdictions the line has to cross. A transmission line that runs from, say, Wyoming to California might pass through multiple states, each with its own regulatory commission, its own environmental rules, its own community concerns. And that's understandable. Nobody wants a massive steel tower in their backyard. But it creates a real problem when you're trying to move large amounts of renewable energy from the places where it's abundant to the places where people actually live. This is one of the reasons HVDC technology, which we talked about earlier, is becoming so important. Those high-voltage direct current lines can carry enormous amounts of power over very long distances with relatively low losses, and because they can be buried underground or run undersea, they sometimes face fewer permitting challenges than overhead AC lines. Projects like the Swedlink in Germany, which will carry wind power from the north to industrial centers in the south, or the proposed SOO Green Line in the United States, running underground along railroad rights-of-way from Iowa to Illinois. These represent a new approach to the old problem of moving electrons from point A to point B. And storage, of course, is the other big piece of the puzzle. We mentioned Hornsdale in Australia, that 100-megawatt lithium-ion battery that proved utility-scale storage could respond faster than any gas turbine. Since then, battery installations have scaled up dramatically. California's Moss Landing Energy Storage Facility, which came online in stages starting in 2020, has a capacity of around 400 megawatts and can store enough energy to power hundreds of thousands of homes for several hours. But lithium-ion batteries, as good as they are for short-duration storage, a few hours, aren't necessarily the answer for longer durations. If you need to store energy for days or weeks, to bridge, say, a prolonged period of low wind and cloudy skies, you need something different. That's where some really creative engineering comes in. There are companies working on iron-air batteries, which use the rusting and unrusting of iron to store and release energy. Incredibly cheap materials, potentially very long duration. There's compressed air energy storage, where you pump air into underground caverns when you have excess electricity, and then release it through turbines when you need power back. There's green hydrogen, using surplus renewable electricity to split water into hydrogen and oxygen through electrolysis, essentially the same process Nicholson and Carlisle stumbled onto in 1800 with Volta's pile, and then burning the hydrogen or running it through a fuel cell later to regenerate electricity. The round-trip efficiency isn't great, maybe 40 to 60%, but if your input electricity is essentially free surplus from wind or solar, the economics can still work. And the beautiful thing about hydrogen is that you can store it for months. You can move it through pipelines. You can use it in industrial processes that are hard to electrify directly, like steelmaking or cement production. So the grid of the future, and honestly, the grid that's already being built right now, piece by piece, looks very different from the one Edison and Tesla and Insull created. It's more distributed, more flexible, more intelligent. It has millions of sensors feeding data to algorithms that optimize power flows in real time. It has batteries and demand response systems that can absorb fluctuations that would have caused blackouts a generation ago. It has power electronics, those descendants of the old mercury arc valves and thyristors, switching and converting and controlling current with a precision that would have seemed like science fiction to the engineers who built the first AC systems. But here's the thing I keep coming back to, and maybe it's the most comforting thought to end on. For all the complexity, for all the sophistication of modern grid technology, the core of it is still startlingly simple. A magnetic field changes near a conductor, and electrons move. That's it. That's Faraday's law. That's the heartbeat underneath all of it. Every wind turbine spinning in the North Sea, every solar inverter on a rooftop in Arizona, every massive generator in a hydroelectric dam, they're all variations on that one principle. A changing magnetic field pushes electrons through a wire. Michael Faraday figured that out in 1831 in a small laboratory at the Royal Institution in London with hand-wound coils and an iron ring. And nearly 200 years later, we're still building a civilization on that discovery. There's something deeply satisfying about that, I think. In a world that can feel overwhelmingly complex, where the technology around us seems to multiply and accelerate beyond comprehension, it's nice to know that underneath it all, the physics is elegant and knowable. You can trace a line from Thales and his amber, through Volta and his battery, through Ørsted's compass needle deflecting near a wire, through Faraday's spinning motor and his law of induction, through Maxwell's beautiful equations and Hertz's radio waves, through Edison's Pearl Street Station and Tesla's polyphase motors, through the vast interconnected grids that span continents today. And it's all one story. One long, winding, deeply human story about curiosity and ingenuity and the stubborn desire to understand how the world works and then use that understanding to make life a little better, a little brighter, a little more comfortable. And right now, at this very moment, that story is still being written. Somewhere, an engineer is debugging code for a grid management algorithm. Somewhere else, a technician is connecting a new battery array to a substation. Somewhere, a researcher is testing a new material that might make power lines more efficient, or solar cells cheaper, or transformers smaller. The work goes on, quietly, mostly out of sight, the way the best infrastructure always works, invisibly, reliably, in the background of your life. So as you drift off, if you haven't already, just know that the grid is out there, humming along, doing what it does. Generators are turning, electrons are moving, slowly, just a few centimeters per second in the wire, but the electromagnetic wave that drives them travels at nearly the speed of light. Transformers are stepping voltage up and down. Power electronics are switching on and off millions of times a second. Algorithms are balancing supply and demand across distances that would have been unimaginable to Faraday or Edison or Tesla. And all of it, every single bit of it, rests on principles that you now understand. That a changing magnetic field creates an electric field. That current flowing through a wire creates a magnetic field. That energy can be neither created nor destroyed, but only transformed from one form to another, passed along, shared, delivered to exactly where it's needed. That's electricity. That's the whole story, from amber to algorithms, from a spark in a darkened laboratory to the quiet, steady current flowing through the walls around you right now. And it's a good story. One of the best, really. The kind of story that rewards a slow telling, that reveals new layers the more you think about it, that connects the ancient world to the modern one in a single, unbroken thread of human curiosity. Sleep well. The grid's got it from here.